I am going to present you the contribution of Aristotle University of Thessaloniki and particularly the WinFOS Research Group in MASSTART Project. And we're going to talk about the development of the testing automations of high-speed silicon photonic transceivers, which are used in data center interconnect applications. As it has already been mentioned, the main goal of MASSTART is to provide a holistic transformation to the assembly and characterization of high-speed photonic transceivers in order to lower the cost for mass production. And Aristotle University of Thessaloniki participates in that, mainly in the part of the enhancement of automated testing in photonic integrated circuits. In this part, the main need is the reduction of the characterization time of the wafers by a factor of 10, while at the same time having yield analysis higher than 90%. And for that reason, an automated die testing platform for transceivers has been developed. In particularly, our collaborators from Ficontech, they have provided us with a die tester probe setup, which we used for automation of various characterization tasks. I can show you with a laser pointer. Okay, you can see this probe here in the pictures. The main components of it are the two mechanical XYZ stages, which are used for the fiber probing. It also includes camera, a top view camera, a hexapod behind here, which is used for the RF probing, and it also contains a vacuum chuck for die stabilization. In AUTH, we have used this probe in order to develop a fiber-to-fiber alignment automated process, which includes many sub-processes, and the first of them is the fiber calibration on grading couplers. With this process, what we actually do is that we calculate the fiber's height by using an autofocus tool, which varies the camera's height. We combine this with the second step, which is the chip calibration. At this stage, this sub-process, we are able to, using the same tool, the autofocus tool, and selected a specific region of interest, we calculate the height of the chip. So by having the knowledge of the fiber's height and the height of the chip, we are able to calibrate the fiber's XY positions on top of the chip. We combine that with the third sub-process, which is to find the initial alignment positions. In order to do that, we use the shape editor, which is implemented at the process control master, which we were also provided with. So we give to our system a shape that contains all the grading couplers. In order to recognize them, we focus the camera on the chip in order to detect the shapes that we have inserted. We move the fibers to the reference positions that we have set it. For example, you can see here at the beginning of the grading couplers. And by having the knowledge of the exact distances of the input and output grading couplers, we hard code also the distances of the rest of the grading couplers of the die tester. And that way, the system recognizes not only the first one reference position, but also the rest of them. So by sending our fibers actually to the initial alignment position, we are now ready with the fourth sub-process to find the optimum link. And we use that, as you can see, with the process that you can see here in the picture. So we have the fibers on the alignment positions, and we use scans in order to find the optimum link. The scans include scans over the x-axis and the y-axis. And here in the scan, you can actually see with the color coded, you see the power losses that we detect. and that way we understand if we do have an optimum link or not. So far, with this process, we have achieved a link with 11 dBm losses in less than 2 minutes. Following the same concept, we are now developing a process for RF probing, which is also automated. That process, we have created the first sub-process, which includes the calculation of the exact distance that we have to bring the RF tip on the chip in order to have the electrical connection. We do that with, so far, with a deviation of some tens of micrometers from the exact distance. And the next step, following the concept like before, would be to automatically recognize the shapes that we want on top of the die tester in order to do more efficiently the electrical connection. The probe tester that we have also used it for the evaluation of silicon photonic transceiver dies that we have received from our partners. In particularly, as you can see here in the pictures, we have been provided with a 4-channel silicon photonic transceiver with Mach-Zehnder modulators. The components of interest for the evaluation were the grating couplers, you can see on the left and the right, or more clearly here. And also the Mach-Zehnder interferometers. We have 4 of them. Each of them contains two phase shifters and also 2 thermoptic phase shifters. The measurements that the university has performed are optical, with the process of the fiber-to-fiber alignment that I have showed you before, and also the electrical measurements on Mach-Zehnder modulators, which includes VNA measurements on the phase shifters and also optical modulation in no band. For the VNA measurements, we have specifically focused on the 3rd Mach-Zehnder interferometer and at the 2nd phase shifter that you can see here. So we have executed S11 electrical measurements for different voltages of reverse biasing of the Mach-Zehnder modulator, and we have successfully received the signal that you can see here. And additionally to that, we have performed S21 electro-optical measurements for different voltages. And with that, we were able to calculate the 3 dB bandwidth of our testers, which varies from 16 gigahertz up to 22, from 0.5 to 5 voltages reverse biasing, respectively. Finally, we have also executed optical modulation with NRZ and PAM4 signals. So on our probe station, except from the 2 fibers, the RF probe, we have additionally included a DC probe on a separate stage, and that way we were able to execute NRZ and PAM4 measurements for specific values of reverse biasing and biasing of the thermo-optic element. In order to conclude, in the future, we will optimize our fiber-to-fiber automated process for die testing. We will reduce the optical power losses below 8 dBm and also reduce the scanning time to less than a minute. There are some possible ways to do that, and one of them is to scan with the 2 fibers independently. So first with the left fiber and after that with the output fiber, separately in x-axis and separately in y-axis. Or we could also use combinatorial scanning shapes such as spiral, so as to find more accurately the link position. Also, we will optimize the RF probing electrical connection. So we aim to calculate with less deviation the distance for the electrical connection, and we will also develop the process for measurements of specific elements on the chips, for example, on Mach-Zehnder modulators. With that, I would like to thank all the partners of MASSTART for the nice collaboration we have. And I would also like to thank my group, WinFos Research Group, and of course all of you for your attention. Thank you.